Welcome back. In this video, we're going to look at the problem of classifying data and see once again that that relates to representation with matrices and the use of matrix multiplication. So our goals are to introduce the classification problem, define what we mean by a linear classifier, and then write the problem of supervised learning for the linear classifier weights in terms of matrices. Classification is the problem of assigning a category to data. For example, you may have some photos and wish to decide whether a face is happy or sad. So you're trying to categorize the photo as either representing a happy face or a sad face, even though that may be different people. So the way that we do this is we extract features from the data based on a model. We're going to keep this really simple, and I'm going to assume that the width of the mouth and the height of the corners relative to the center of the lip is a good indicator of whether someone is smiling or frowning. So we might expect that if the mouth is wider and the corners tend to be elevated relative to the center, that the person is smiling or is happy. Whereas on the other hand, if the mouth is narrower and the corners are somewhat lower than the center, the person may be sad. So if we call these two measurements x1 and x2, we collect x1 as the width and x2 as the relative heights, we could plot a bunch of examples in this two-dimensional coordinate system. And if we use pluses for happy and minuses for sad to indicate different photos that we have access to, we might get something like this. So it looks like the faces which are happy generally tend to be wider, and the corners tend to be higher than the center of the mouth relative to the cases of the sad faces. So the goal of classification is to find a boundary so that we can make a decision. We might decide, if I get a new data point and it lies over here, is that a happy or a sad face? Well, if we have a boundary, we can decide that points above that are happy and points below that are sad. Now, we might not always get it correct, and that we might have some misclassifications, like in this example here, where this smiling face ended up below the boundary and thus would be classified as being sad. So let's continue the idea of having a straight line to separate the classes like we depicted on the previous slide. We know that the equation for a line is x2 is equal to mx1 plus b. So we've got a slope m and intercept b. So the problem of finding our classifier is equivalent to finding the slope m and the intercept b. Now I can also write this equation as x2 minus mx1 minus b equals 0. And in this form, I'm going to rewrite this boundary as an inner product. So we'll collect our feature, in other words, x2, x1, and I'll put a constant here because I have this constant for this intercept. We'll have a feature vector x. We'll have a vector of classifier weights w, which are going to be related to the slope and the intercept. And then I can rewrite this equation as the inner product x transpose w equals 0. So our goal in this is to find a w. And once we know that w, then this equation will give us the decision boundary. Now we did this for the case of a decision boundary that was a line, but you can do this with curved decision boundaries by generalizing the definition of the feature. For example, we could have a cubic shaped decision boundary if I include x1 cubed, x1 squared, x1, and 1 as part of the feature vector. And that gives us additional parameters in those classifier weights that need to be identified in order to determine what the boundary is. But still, this general form of the inner product of the feature with a set of weights equal to 0 is going to give us a decision boundary. So a linear classifier makes a decision based on a weighted sum of features. Now those features can be nonlinear functions of the measurement. In x, I can have a nonlinear function of any particular measurement or data point that I collect, but the important aspect that makes this a linear classification problem is that x is some known feature and I have a weighted combination of this feature with a classifier weight vector w. Now we use labels to define the class associated with each feature. So in this problem we've been looking at, we're trying to decide between a happy and a sad face. I'm going to assign the plus symbol, or happy faces, I'm going to say those are labels +1, and we'll assign a label of -1 to the sad faces. Now, use of plus and -1 is somewhat arbitrary here, but it turns out to be very convenient in this problem when we're doing binary classification. That is, we're trying to make a decision between two categories. Given a set of data or features and the labels that are associated with those features, I can set this up as a supervised learning problem. And my goal is to take these given features and labels and find a set of classifier weights W so that this inner product xi transpose W is approximately equal to the known labels. We can reformulate this supervised learning problem as a system of linear equations. So if I collect all of my capital N training samples into a matrix whose rows represent the features, so I have x1 transpose, the first feature, times W, and I want that to be equal to the label for the first feature. Then I have x2 transpose times W, and I want that to be approximately equal to the label for the second feature, and so on until we get to the last training sample, xn transpose times W, and I want that to be equal to the label for the nth training sample. So this leads to a system of linear equations where I have a matrix X times my classifier weights W equal to the vector of labels L. If I have n training samples and each of those features has m components in it, then X will be a n by m matrix, W will be an m by 1 vector, and of course L then is an n by 1 vector as well. Once I solve this training problem, in other words, I find a good set of classifier weights using the data, the training data that I have available, then if I have some new candidate feature, x tilde, that I want to classify, I'm going to use my known weights that I found to classify it. So I would compute the inner product of x tilde with those weights, W, and if it turns out to be greater than 0, then I'm going to assign the label 1, say it was in category 1. If that inner product is less than 0, then I'm going to assign the label -1. So that's the essence of the binary classification problem. There's several important questions and issues that we'll address later. One of those is, what do we mean by approximately equal to? So how do we measure the closeness between capital X times W and our set of known labels L? We also have seen that there's different ways to choose the features, and that can lead to different boundary complexities. There's a trade-off that we'll have to explore in terms of how do we choose an appropriate set of features and corresponding boundary complexity for a given problem. Both of these questions end up being intimately tied with the idea of performance evaluation. Ideally, we'd like to minimize the number of misclassifications. And then extending this problem beyond the case of binary classification, in general, we want to classify capital M different categories. We call that M-ary classification. So I've illustrated a three-way classification problem in this sketch where we're trying to separate the categories associated with the minus signs, the plus signs, and the circles. So we might be trying to find some set of decision boundary that is sketched, such as sketched here in orange.